All right. Hi, everyone. Thank you for joining us. Welcome to the Basic Concepts of Earthquake-Resistant Design and an Introduction to U.S. Seismic Regulation. This is a webinar presented by the Applied Technology Council, FEMA, and EERI Student Leadership Council. EERI, the Earthquake Engineering Research Institute, is the leading nonprofit membership organization connecting professionals who are dedicated to introducing earthquake resilience around the world. Our members include people from a wide variety of disciplines and at different stages in their career. And this webinar in particular is being hosted by the members of our Student Leadership Council. So I'm going to turn it over to today's moderators, Khalid Saifullah and Ahmed Hassan, who are the co-presidents of the SLC this year, and they'll introduce the other speakers today.
Hello, everyone. On behalf of Student Leadership Council of SLC, Student Leadership Council of EERI, I welcome you all to this webinar. Today we have Gigi Rojan, Assistant Product Manager from ATC, and Pataya Scott, a civil engineer from FEMA, who will be giving the introduction to our presenter, Michael J. Griffin. We thank FEMA and ATC for organizing this webinar for all of you. Yeah, with that, I will hand it over to Gigi.
Great. Thank you. Hello, everyone. My name is Gigi Rojan. On behalf of the Applied Technology Council, I'd like to welcome you to this webinar series on FEMA P-749, Earthquake-Resistant Design Concepts and Introduction to the Seismic Provisions for New Buildings. Today's webinar will be on Part A of the FEMA P-749 report, which serves as an introduction to seismic-resistant building practices in the U.S. This webinar is the first of a two-part series, and if you haven't already signed up for next week's webinar, we highly encourage you to. It will be presented by Ron Hamburger and provide technical considerations for the seismic design process. The training material for this webinar was recently developed by the Applied Technology Council under a contract with FEMA, the Federal Emergency Management Agency, and this is the first time we'll be delivering it for a live audience. Therefore, we would greatly appreciate any feedback you have to improve the training material. Please make sure to fill out the survey poll after this webinar and look out for another post-webinar survey sent to your email within the next week. These training materials are drawn from the new edition of the FEMA P-749 report, which expands upon and updates the previous edition to the most up-to-date seismic provisions. The new FEMA P-749 report will be coming out later this year, so please keep your eyes open for the report in the coming months and make sure to download once it's available. Now I'd like to turn it over to Pataya Scott, who will provide a brief introduction to today's webinar. Pataya is a civil engineer at FEMA's Earthquake and Wind Programs Branch and is the project officer overseeing the training and development, as well as the new edition of the FEMA P-749 report. Pataya, please go ahead.
Thanks, Gigi. Good afternoon. As she said, my name is Pataya Scott, and I am with the Federal Emergency Management Agency's Earthquake and Wind Programs Branch. So it's my pleasure also to welcome you to today's training. As part of our responsibilities under the National Earthquake Hazard Reduction Program, FEMA supports activities to reduce future earthquake losses. And the primary way we do this is through the development and publication of technical design and construction guidance products, as well as through the support of training and related outreach efforts such as this training. FEMA supported and worked with the Applied Technology Council to develop this training course to provide a tool that communities and other entities could then use to encourage greater protection from earthquake hazards, thereby reducing future earthquake losses. Understanding the basis for seismic regulations and the nation's building codes and standards is important for design professionals, students, building owners and operators, and many others. So we hope you enjoy Part A of this webinar. Thank you.
All right, thank you, Pataya. So now I'd like to tell you about our fabulous presenter today. His name is Mike Griffin, and he's the president at CCS Group in Missouri. He has over 35 years of extensive experience in assessment of earthquake and high wind for structures and non-structural components, equipment, and systems. He routinely provides trainings and education sessions to engineers, management personnel, and students in natural hazards and risk assessments. He is one of the lead developers of this training and was the reviewer of the FEMA P-749 report. All right, Mike, go ahead.
Thank you, Gigi. Well, hello, everybody. Let's get started right away because we have a lot of material in this section for an hour and a half. P-749, as it was stated, it's in the updated process, be delivered later this year. This is a draft cover copy of it. It's leveraging off of a 2010 version of this document and expanded. We've broken it into two different parts. One for the general public to give them an understanding of the building code regulations relative to seismic safety, and then more of a technical part that's more geared towards design professionals and really understanding what the seismic design provisions in the code are all about. And so that's part A and part B. Today, we're just going to do part A and briefly talk about earthquakes and their effects. We'll talk about the building code and development process. How do our seismic provisions get into the building code? We'll talk about acceptable risk that's inherent in utilizing the building code for structural seismic design. Then we'll leverage into a little bit on resilient design to where we can hopefully move people towards a greater degree of seismic performance than the code provides for us. Then we'll briefly talk about some important features that are relative to good seismic building performance. What are the things we have to do? And a lot of these elements actually are elements within the building code that a structural engineer has to walk themselves through in order to perform the seismic design. And then we'll end it up with talking about some common structure types and their associated vulnerabilities to give us a little bit of understanding on the relative vulnerability between them. You can see part B there. That's the next session, which is going to be in early or mid-May. And that's going to be more of a technical discussion of those topics. That's going to be performed by Ron Hamburger. But before we move forward a little bit further into our topic today, I'd kind of like to get a little bit of understanding of your background as an audience. And so the question here is, what level of experience do you consider yourself knowledgeable about relative to building code, seismic design provisions? So very little knowledge, the first question. The second is a basic understanding. So you might be in an architectural program or a mechanical engineering program, not necessarily structural. So you understand there is seismic design provisions in the code. That's you. Beyond that, the third one is you're a structural engineer or studying structural engineering, and but you're not that familiar with seismic design aspects relative to that structural design concepts. And then lastly, you have a high level of experience that you do seismic design all the time. That's the nature of the question, just to give me an understanding of background of our audience today. So go ahead and weigh in. I'm looking at the results and nobody has very little knowledge, which is great. That's fantastic. Majority of you do have some level of experience with structural design, but not necessarily seismic. And then in second place coming up is, I see basic understanding of the code provisions, that there's provisions in there for seismic design, but you're not that familiar with it. Okay, and several of you, let's see, 9 out of 41 have a high level of experience. Okay, for those of you in the high level, this is probably going to be very easy, it's basic understanding of these provisions. But the rest of you should benefit from our session today. Let's see, can I do that? Does everybody see the results? I'm assuming yes. Okay, all right, let's move on. So chapter 1 in our document under part A is earthquakes, effects, and their impacts. So some basic concepts. The USGS detects roughly 20,000 earthquakes worldwide. They generally occur along our tectonic plates, as you can see in the figure to the right. Most of these are very small earthquakes, and a lot of them are not felt, but a few people may feel them if they're within close proximity to the epicenter. But there are some large ones that can do some pretty destructive damage to our built environment. So why do the earthquakes occur? Well, we've got a molten core of our Earth with a crust, thin crust on top of that, think of it as an eggshell. It actually can crack and break. Well, due to the tectonic plates that make up that crust, they're pieces. And so as the Earth rotates, we have gravity acting, and those forces, we can actually begin to move those plates relative to the adjacent plates along those tectonic boundaries. And we can create friction or lockup that at times releases, and then that imposes or causes an earthquake generally along those tectonic plates. We can have intraplate earthquakes that occur, which we'll see here shortly. And that's what you see here in the earthquakes. And this was just from March of this year from the USGS website of earthquakes that have occurred. And so you can see it's quite a large number. Now, most of these are small, not very perceptible. You can see we have these intraplate earthquakes in the middle of the US, right there in Oklahoma. Those are generally caused by fracking, not our tectonic plate environments like we see on the West Coast there. But these are small generally. So what are some of the earthquake effects that affect our built environment? Well, there's fault rupture, there's ground shaking, landslides, liquefaction, and lateral spreading. So let's take a look at each of these. So for faulting, if we've got a fault system that rises up to the surface completely through the crust and exposes itself, and we have a building that is constructed across that, that's going to have a greater impact than if we have earthquakes that occur down deep within the crust and that tectonic fault doesn't rise up to the surface of it. So it's just going to be shaking involved. But if we do have faults that rise up to the surface, it's going to be more impactful to our built environment. Those can be of a variety of them. We can have a vertical or subduction zone fault, which is the upper left. That's where a plate tries to ride underneath or dive underneath an overfault so we can get some vertical motion out of it. We can have a strike slip fault or lateral, the shifting of those tectonic plates relative to each other. And then we can also have tectonic features that pull apart. And we can also have a combination of all of these as well. So as faulting goes, we like to understand where we have surface faulting, so we don't construct and design buildings on top of those features, because I can guarantee the building will not restrain the fault. Here's a couple of good examples. Left photograph shows a horizontal offset. You can see the offset in the fence, and the right shows a vertical offset. This happens to be, not sure of the earthquake, but it's in Nevada, where we've got a pretty dramatic vertical offset. Notice the building just out of harm's way there with this example. The next effect is ground shaking, which is our most prevalent hazard associated with earthquakes because it affects a very large geographical area. If you can imagine, faulting and the other hazards we're going to look at are very defined in terms of geographical area. And so they're not going to affect things outside of that small geographical footprint. But ground shaking does. It affects a very large geographical area. And it's very much like ripples in a pond. As the ripples move away from the cause or the stone that we threw in there, those waves die down or attenuate as they get further away. Earthquakes are no different. The energy that's released from the earthquake, as we move further away from that epicenter, we can actually, the ground motion attenuates or dies out. And so it becomes less damaging or impactful to our built environment, as shown here by the damage from left to right, getting worse to better performance of our buildings. However, we can have buildings that are founded on poor soils. The lower right is an example of that, to where we can re-amplify or amplify the energy that's moving away from the epicenter to damaging levels to our built environment. Some examples for what type of soils that would be. Think of riverine valleys or floodplains that have cohesionous soils. They're saturated with water. And so we can re-amplify that energy to damaging levels. The lower left here is hard rock. The energy just transmits through very efficiently. It doesn't generally amplify, it generally de-amplifies. And so that's a much better soil environment for us to found buildings than it is for some of these other soils. So you can see by the time histories that are shown there and the amplitude of those, the difference between hard rock and the other less competent soil materials, that becomes a very important parameter that we have to understand our building is founded on when we look at it from a seismic design perspective. Now, as far as measuring earthquakes, there's Richter Magnitude, which is the one common one that everybody seems to understand to some degree, but it really doesn't tell us anything about the damage potential from the earthquake. For example, if we had a 9.0 earthquake that occurred out in the middle of the Pacific Ocean on an intraplate boundary, does that really mean anything to us? It's so far away, the energy by the time it gets to us here in the States, for instance, it's not even going to cause any shaking. We're going to know what has occurred from the USGS, but it doesn't cause us any damage. So Richter magnitude only tells us the amount of energy that's released. Now, the larger the greater the number, sure, we have a higher magnitude, so we're going to have more energy, therefore greater potential for damage, but it tells us nothing specifically about the damage to the buildings. It's a logarithmic scale, so going from from a 4 to a 5 in terms of Richter magnitude, that's a 32-fold increase in the amount of energy released from the earthquake. It's logarithmic. So we can have some dramatic effects within very small ranges of magnitude number. And this figure here shows the Loma Prieta earthquake of a 6.9 relative size to scale and the amount of energy released compared to the 7.8 1906 earthquake, which is significant amount of energy released. And so it's a logarithmic scale. Now, something that is more informative is an intensity scale or modified Mercalli intensity. It's a scale of 1 to 12. It's qualitative in nature. And what it does is it describes qualitatively what the damage was at your particular location. And if you haven't done it already, I encourage you, if you go to the USGS website and there's a link there for You Felt It. It's called You Felt It. If you feel an earthquake, you can actually log in there and go to the You Felt It page, and it'll ask you if you felt an earthquake. You can answer a series of questions. Those questions are related to the modified Mercalli intensity scale. And then the USGS can then map that in terms of what people felt from that particular earthquake relative to their distance from the epicenter. And it's kind of interesting. You can look at all past earthquakes and kind of see. Now, what this does is it takes into consideration soils. And so we can have buildings founded on poor soils that have damage, and just up a hillside on rock, for instance, we can have buildings that perform very well. And so the intensity level is going to be much less, say a 4 or 5 versus 6 or a 7, where we start to see structural damage. So intensity is a little bit more informative in terms of the information that it provides. And emergency managers, government officials, all utilize modified Mercalli intensity to understand the impact from the earthquake, because it does gives us an idea of the damage experienced. However, that's not good for us in engineering, where we have to design buildings for seismic. We like to have the actual measurements of the ground motion at our particular building sites where we're doing design. And so it's a displacement time history, the velocity time history, and the acceleration time histories that we're interested in. We can take those and then apply those into our building structural models, and then utilize those to actually design our buildings or see how our buildings respond to this particular earthquake that's developed these traces here. So you can imagine the duration, the magnitude, as well as the frequency of the energy within that is different from earthquake to earthquake. And so generally what we do for structural engineering is we take a family of these types of records and then apply those to the building to see how our building responds, and then design accordingly. Landslides, that's another earthquake effect we need to worry about. Again, this is due to the geological and soil parameters underneath our building to where we can actually engage the soils to where we start to loosen them up, and then they slide just based on loads. And building on the right, where we lose bearing strength, and it just slides down the slope because that's the least resistance, and as well as the one on the left. Liquefaction due to poor soils is also another element we worry about in terms of our soils. Again, poor soils, riverine valleys. You need three things to liquefy soils. You need poor soils, you need a high water table, and you need to shake hard. So three things. We got a lot of buildings right now that are in riverine valleys and floodplains that are sitting on poor soils with high water tables, and they're doing just fine. Well, it's the third element that we need to induce liquefaction, which is a loss of soil bearing strength. And if it's underneath our building, now we can start to cause displacements or settlement of our building foundation systems. Could be minor, it could be severe, we could overturn buildings. Think of quicksand. That's really what liquefaction is. It's a loss of soil bearing strength. And if we found our buildings on those, then we're going to potentially have problems. Here's a good example of liquefaction where we've got an underground sewer line that essentially, due to liquefaction, the high water table was floated out of the ground as a result of the shaking from the earthquake. We can have lateral spreading. So again, slope and poor soils, that we can actually begin to pull apart and lateral spread some of these elements of our built environment and infrastructure. If we look at how do we use this information in our design, the USGS performs a seismic hazard analysis. And what they do is they look at the historic record of earthquakes on the various faults that they mapped. There's still faults they haven't mapped. And so there's research always being done and performed on this. They look at the most active faults and also inactive faults as well to understand, hey, are they capable of causing a large earthquake? They look at the frequency of these earthquakes. What's the relative or the magnitude of these earthquakes as well in terms of completing our entire picture of the seismic hazard around particular geographical locations where we found our buildings. Again, they look at the amount and intensity of shaking, the magnitude relative to the event, and geographical region that's going to be impacted by the event. And they can then provide maps or seismic maps of these different areas at different return periods. Typically our standard are the 475 or 10% 50, the 975, which is 1,000. And then what's in the building code is our 2,400 year return period that we utilize for seismic design. And that's our ground shaking level of which we apply to the buildings, our buildings for design. If we can take that and kind of put it more into a little easier to understand context of seismic risk or intensity, here's a map that represents the 2,400 year return period, which is what's in the building code relative to our seismic hazard, ground shaking hazard. And you can see the white areas are minimal or no shaking. And the other areas, as we go towards darker colors, represent the stronger level of shaking and therefore higher potential for damage, and also greater requirements for seismic design that are inherent in our building code design provisions. So with that, if you want to learn any more information, good resources, USGS or the FEMA websites to obtain much more information. Remember, anything with FEMA's name on it is free. And there's a lot of good documents and research and guidance that's published within those FEMA documents. So I encourage you to access the FEMA website, ready.gov/earthquakes, and you're going to see a wealth of information there and reports. Recently, it issued one on home safety is FEMA P-749. That's shown there. These are downloadable off the website for free, as well as I think they have some hardbound publications if you want to order them. All right, let's jump into chapter 2 and talk about building regulations and acceptable risk. If we kind of generally go through the building process and how that there's a lot of players involved. A building is conceived by usually a developer or an owner. There's other people involved with that. There's the lenders, there are insurers for that. Once that's established, and then the developer owner engages design professionals to actually design the building and project their vision of what they're thinking it should be. That's architects and our engineers. Then we build the structure. So that's going to be focusing on our contractors. They have a construction manager, general contractor, and subcontractors. Then we got regulators. That's our building officials and also our inspectors. Associated with that is within the code, our special inspectors and testing agencies for specific elements, particularly structural, for our buildings to ensure that our materials and the construction is in compliance with the actual design. Here's a kind of another little slide of the process as well. Developers, owners, again, take the lead. They have the concept. We go to design. We use the contractors for our construction. We have our special inspectors. By code, they're hired by the developer or the owner. They perform our structural tests. There's general special inspections for buildings, and there's also separate categories for high hazard regions for wind and seismic that adds to that special inspectors are involved with. And then there's the building officials. They're responsible for conducting plan reviews that are submitted by the design professionals for the building. They can conduct inspections. They provide building permits as well as occupancy permits for the building. And so when we look at the purpose of the building codes, they're adopted and enforced by local government. We'll see a different slide here later with what kind of reinforces that, why that's by state and local government. There are a set of minimum requirements. That's a key element here in understanding the acceptable risk that's inherent in the building code design provisions. And so just keep that in mind as we move forward here. The building code assures that we've got public safety key point in mind, and that developers and don't cut corners to try to save money. So it's a public safety document for our building codes. Most jurisdictions, we call them AHJs, authorities having jurisdiction. That's our local communities. It could be a city, municipality, it could be a county, it could be a state, that all could or may adopt a building code or have a building code. Most of those jurisdictions adopt a model code. The model code is an international, today is the International Building Code. And so many municipalities or HJs will adopt the model code, but they might tweak it a little bit with amendments and say, well, we don't like this, do it this way, that sort of thing. So it's generally adopted as is with amendments. And it's developed by the International Code Council, and there's a family of building codes that are developed. There's the International Building Code for building construction. There's a mechanical code for mechanical systems, plumbing for plumbing systems. There's a whole host of ICC codes that are part of the family of the building codes. Interestingly, in the US, the model code through the ICC is developed by private organizations. It's not government driven, versus if you look at regulations outside of the US and other countries where they're government driven and developed. And so they're developed by private organizations. The technical provisions in the code as well are developed that way through consensus standards we'll talk about. And that's where we have design professionals and we have professional organizations like the Structural Engineers Association, and American Society of Civil Engineers that have representation on these committees, volunteer committees, to help with the development of the technical provisions. Anyone can actually submit questions or changes to the model building code to ICC. They may not be heard and addressed, but you can submit. And so here's just showing a collage of the municipalities that have taken the IBC or model building code and then incorporated that to suit their particular needs. So Seattle, Chicago, New York, and they'll throw a different cover on it. California has a California building code, and the basic structure is they start with the model code and then they modify it to suit their particular needs. When we look at building regulations and building codes, all the codes are not enforced consistently across the board. For example, if you've got some municipalities that adopt the code and it has seismic provisions in it, they haven't exempted them, but they're in a more moderate seismic environment, particularly, let's say, the Midwest, where I'm from out here in St. Louis, to where they don't enforce the seismic provisions within the code very rigorously, if at all. Versus if you have a building that's constructed out in California, where you have a much higher, more frequent earthquake hazard than you do in the Midwest, their building officials enforce the seismic provisions of the code much more rigorously than we do out here. So just because you have a building code doesn't necessarily mean that you are going to have good enforcement of the codes. So adoption is one thing, enforcement is another, which is very key. If we look at older model codes that were developed, and I can go into the three of them, the three basic that were there at the time. Generally, what they did was they took the material standards, material provisions, and incorporated them within the building code. And so the building code ended up being, it continues to grow, but continues to be like this. Whereas today, the various industries, concrete, masonry, steel, and wood, back years ago established organizations and began to developing their own technical guidance documents associated with their particular material. And those then resulted in developing them into consensus standards using the ANSI criteria in terms of the development of those. ICC, as developing the model code, began to look at that, and instead of putting all of those guidance documents that they wanted into the code, they basically said, let's just reference the consensus standards that have been developed as part of our code. And so the IBC has actually shrunk a little bit with that regard, because then there's now the consensus standards that they reference directly, which has been nice. So here's some of those consensus standards. ASCE 722, which predominantly our talk part A and part B later is referenced to, is ASCE 722. That's our Bible for structural design and seismic design for building construction. There's a ACI 318 for concrete. There's the NDS standards for wood, and then also AISC for steel buildings. Like I mentioned, I think earlier, the codes are a life safety code. So there's many aspects to the code than just structural seismic design. And so they're looking at structural stability, fire, egress, ventilation, plumbing, mechanical systems to provide a safe and healthy environment within the buildings, energy efficiency, and natural hazards. They're covering more than just seismic. So the building code is all encompassing with that regard. I mentioned before, once adopted by the state or local governments, it becomes law, technically. Then it becomes enforceable. The enforcement is generally by a government official. It can be a building official, the chief building official. It can be delegated to a fire marshal. Oftentimes in smaller municipalities, that's what you'll see. The fire marshal acts as the enforcer, if you will, or inspector for the building code for that municipality. You can have the clerk actually do it. All of those elements are individuals above there, depending on what they're called, form the authority having jurisdiction for building design and construction. So we refer to them as AHJs. If you look at, I mentioned this earlier, technically it's illegal to construct a building without the AHJ's approval. They do that by reviewing the design drawings and issuing a construction permit. Then they'll have periodic inspections per the code associated with that building to ensure conformance with the design and the plan review that they've issued. Once they've issued the building permit, the construction starts. Once construction is complete and all inspections have been completed and they found in conformance with the building design drawings or documents, then they'll issue an occupancy permit. This whole process here varies from jurisdiction to jurisdiction. Some will require a building permit, others will not. So it's just a matter of resources within the jurisdiction. So you can imagine smaller municipalities or HJs are not going to have quite the resources as a large municipality like City of Los Angeles is in terms of enforcing the building code. So I mentioned this earlier, a permit is issued for construction. After all the inspections have been performed satisfactorily, then the HJ will issue an occupancy permit. Additionally, if we've got triggers during the life of the building that cause for potentially unsafe conditions, the HJ can actually pull that occupancy permit and deem the building unsafe, and everybody will have to evacuate out of the building. So that's in their purview as well. So let's talk about acceptable risk and what is inherent in the building code philosophy in terms of design. So when we have a building, the building has to be identified into a series of risk categories, of which you're accepting a certain level of, for seismic, you're a certain level of seismic performance associated with each of these categories. So risk categories 1 or 2, it's predominantly life safety for earthquakes. It doesn't mean no damage. So you are willing to accept some level of damage at high levels of ground shaking at our design basis that we're designing the building for, if that were to occur. You're going to accept it, but it's not life-threatening. The earthquake shaking stops, the building is damaged, but you should be able to safely egress out of the building. That meets the life safety performance intent inherent in risk category 1 and 2. But what we're trying to do is prevent collapse, because that causes fatalities. And so it's a life safety performance. Interestingly, as we walk through these, keep in mind risk category 2 is where probably 90% of our building stock today would be classified or is classified is in risk category 2. And so just understand what I just said in terms of seismic performance, that it's for life safety protection, doesn't mean no damage. In fact, you could have damage that's so severe it's economically undesirable to repair and reoccupy the building, and yet meet the performance of risk category 2. As long as collapse hasn't occurred and you're able to safely egress out of the building, you've met the performance objective. Risk category 3 is higher occupancy buildings. Think of schools, large auditoriums, buildings of that nature, to where we want some protection of life safety because we have a large population that's in the building at any given time. We also want to protect against hazardous material releases, so that gets an elevated level of performance that needs to be considered during design. And then risk category 4 is our highest. That's where we have the greatest protection. And think of hospitals in that regard. So we're looking at much greater reduction in damage to the structure. And in fact, we're looking towards trying to achieve a level of post-earthquake function very quickly after the earthquake occurs for a category 4 building structure. So we don't have many in that category. An owner can take a normal office building and decide that they're going to elevate the seismic performance and put them in risk category 4 and certainly design a building for that. That is their prerogative. They can certainly do that. But as a minimum standard, a normal office building would be risk category 2. So again, difference in performance. What about existing buildings? Well, the ICC has a document for existing buildings. Some municipalities will adopt the IEBC or the International Existing Building Code. Others will not. So it just depends on the jurisdiction. I should mention too that not all jurisdictions adopt a building code. There are many states and municipalities that do not have an adopted building code. And so the owners and engineers are free to do whatever they want. There's nothing requiring them to do anything. Some states have adopted state mandatory building codes. California is one of those. Missouri, where I'm here, the state does not have an adopted building code for the state. So the rural areas, county and otherwise, do not have an adopted building code. You can do whatever you want out there. If you're larger municipalities like St. Louis County, where I reside, the St. Louis County has a building code and they enforce the seismic provisions. So it just depends. So keep that in mind. But for existing buildings, we don't. Our building codes are updated every 3 years. And so there's not a requirement in the building code that says, hey, I've now got to reevaluate my building and update it to the latest building code, particularly for structural seismic. There's no such requirement in the update of the building codes. But there are certain triggers that are key that are in the IEBC for those instances that we need to look at much more closely in terms of what we do to the building, because it could be affecting the life safety performance of the building. And so some of those triggers for you to adopt that is we have building additions. So we have to be understanding of how the addition affects the response, particularly seismically, of the existing building. That could trigger us actually performing an evaluation and retrofit to bring the old building up to code based on how we attach or construct that addition adjacent to the existing building. We can have occupancy changes. Let's say you have an office building and it's risk category 2, and you now are going to change the occupancy of that building to a much greater population inside of it, to a category 3. That's an automatic trigger that now you've got to evaluate and bring that building up to current code that is adopted at that time. That's a trigger. If you do any substantial alteration or repair that are affecting the structural members or mass within the building structure, that's another trigger that's going to cause building to be brought up to a higher level of safety, which is current code. There's also provisions in there that kind of put a check on some of those instances where I'm going to renovate this entire building, but I'm only going to do 20% of it in 2 years, and then I'm going to do another 20% in the next 2 years, and so on and so on. The code has a requirement that it's cumulative over a 5-year period, then you trigger this. And so you can't get out of stepping through and doing them over a substantial period of time as well. There's another instance where the upgrade to current code can be triggered, and that is if you have major damage due to natural hazards, fires, earthquakes, windstorm events, or other incidents could cause the building to have to be upgraded when it's reconstructed, essentially. For those buildings for seismic safety that we want to bring up to a higher level of performance, there is a document, ASC 4117, which is the structural engineer's Bible, basically, for evaluating existing buildings and retrofitting them. It's a tiered approach, and it's not bringing up to code, but it's a higher level of performance based on certain performance objectives that are desired for that building. And that's been underdeveloped for a long time, and now it's becoming very mature and used throughout for existing buildings for seismic safety. Some of the municipalities, AHJs, can actually adopt ordinances directly for seismic safety improvements in certain conditions. There are things that are more vulnerable than others, and some of those are unreinforced masonry buildings where you've got parapets that are very prone to collapse during even small levels of shaking. And so some municipalities, particularly on the West Coast, have ordinances where the parapets have to be braced back to the roof structure, so to prevent the parapets from falling over and down to the sidewalk below. That will kill you because of the heavy masonry and bricks that are falling. Non-ductile concrete buildings, these are generally concrete frame buildings that are of older construction or older vintage, pre-1980s roughly. in terms of that. Further back, if you go here to the east, I'm talking West Coast, to where the non-ductile concrete buildings, frame buildings, have shown to be vulnerable during seismic shaking. Tilt-up buildings, particularly wood frame to concrete tilt-up walls, we could have separation of the diaphragm connections with the wall, and our panels can actually fall out if we're not careful. We have the pre-Northridge steel moment frame issue back in '94 that caused a change in our seismic design provisions for moderate and high seismic regions in terms of connections that are able to be used by structural engineers, as well as we've got wood frame buildings with soft stories. West Coast again has ordinances in some municipalities where those have to be retrofitted over the next 10 years. The unfunded mandate, they have to be retrofitted. Those are in ordinances. We can also have voluntary upgrades for seismic safety. An owner can be very proactive and want to improve their building structures. And so they'll initiate the upgrade. Generally what you'll do, you hire a design professional, structural engineer, that will then use 4117 based on the performance objectives desired by the owner, and then go through and design a retrofit. There's some other good tools that are resources are available, FEMA 390, 400, 420, as well as E74 for non-structural component seismic upgrades, which are very good documents. Again, free. It says FEMA, they're free. Download each of those. Another good companion document with 4117 for existing buildings is 547 there. Again, that's free. That provides just great techniques for structural retrofits of existing buildings. A lot of the retrofits that have been done are captured in terms of some of the techniques that engineers have used. It's a great document and great resource for applying 4117. What is the federal government's role in terms of risk reduction? I mentioned the code itself is a set of minimum standards. Well, how's the government fall into play here? Well, the government can't regulate building codes to the states. That's in the Constitution. It's the states and the local jurisdictions that regulate themselves. It's not reserved by the federal government. However, federal government can do certain things to encourage municipalities to adopt the latest building codes, as well as look at greater performance of our built environment. They do provide funding after major disasters, wind, flood, earthquakes, and to where they encourage any of that funding that has to go if municipality has adopted a current building code. Then, hey, then we're more encouraged to give you money to recover from that than if you haven't. So there are carrots, if you will, by the government in terms of encouraging the adoption of current building codes. They're also heavily involved in building code development through the National Earthquake Hazard Reduction Program passed by Congress. And its funding is updated periodically throughout the years and always has been. And so a lot of the materials that the FEMA documents I mentioned there are funded through NEHRP. A lot of the research and technical guidance that goes into those documents are funded by NEHRP. Other elements, the way the government encourages good seismic safety is through research. And we'll see that here in a minute. Developing the resource documents. The USGS does the hazard maps. They also provide money for hazard mitigation grants for states and local jurisdictions for more resistant construction. And then they have training. NETAP training is an example of where the federal responds. So through NEHRP, FEMA has a role kind of overseeing all the elements of it. NIST in terms of researching different techniques and guidance that eventually evolves and then goes into our building code development as we expand and evolve the structural provisions. NSF is a funding source. USGS I mentioned in terms of seismic hazard maps. That's their area of responsibility. So all of this goes into developing and upgrading the provisions within the building code. Here's links to those. Those will be in the notes. I'm not going to dwell on those. If we look at resilient design, I already mentioned the fact that the building code's structural seismic provisions or the building code, is a minimum set of standards. And this is right out of the IBC 101.3, and you can read that. It's life safety, not necessarily for the protection of property. And it's from fire, explosion, dangerous conditions, and a reasonable level of safety to firefighters, emergency responders during emergency operations. So it doesn't say earthquake proof in there. It's a minimum set of requirements. So the requirements in there are balancing quite a few different things. One is life safety protection and cost. If we want to elevate the performance for a 2,400 year return period earthquake, is that going to occur during the lifetime of a building, which is generally considered 50 years? Well, the answer is maybe, maybe not. And so do we really want to be designing for that high level of earthquake when there's a likely probability it may not occur during the life of that building? And so there's a give and take there in terms of the cost to achieve that versus, hey, let's design for smaller level of ground shaking events, maximum considered earthquake, not the largest one that could possibly occur at our particular building site. And let's design in some ductility associated with that. So if this big one occurs, that we've got some level of collapse protection or safety for our building. And that's going to be a much more cost efficient way of providing seismic design for our built environment. And so that's the acceptable risk that requirements are being applied to, particularly for seismic. Building codes, though, we do know, we've got a lot of evidence that if they're applied correctly and enforced and incorporated into building construction, they do save lives. They improve disaster resilience from natural hazards and our built environment. Think of a good one is Hurricane Katrina that went through New Orleans. New Orleans has not recovered population-wise since that hurricane. And so if our buildings were built stronger, you can imagine that the population would have come back because the rebuilding would have been significantly less. And so that's the kind of the thought process is with seismic engineering as well. Should we look at a higher level of performance possibly in terms of our design provisions? That risk category 2 where 90% of our building stock is, I mentioned, should we be looking at category 3 where we have less structural damage due to seismic events? That's being looked at. So if we look at resilient design in terms of some recent natural hazard events, it provides a greater emphasis for us to consider designing to a higher level of performance. These are some pretty big numbers in terms of financial damage associated with them. It's been shown time and time again, communities recover much, much slower when there's a greater degree of damage from a natural disaster. And so this acceptable risk approach is being, again, rethought in terms of relative to building design. Here's a good example from New Zealand, Christchurch earthquake, to where the CBD was severely damaged and a large majority of the buildings were actually had to be torn down. They didn't allow them to be rehabbed and reoccupied. They actually tore them down. So resilient design, there's a strong link between the application and enforcement of our building codes in terms of mitigating catastrophic losses. It lessens damage. Communities are able to recover much, much more quickly. We actually have a much greater reduction in financial input to a community after a natural disaster where the built environment is much better. That recovery cost is huge, but if we take a portion of that and put it in on the front end before the disaster occurs, we have a much greater return on investment with regard to that. So increased performance equals less damage, lower insured losses, lower rates, and a faster recovery. So resilient design is a very key thing in terms of looking at our built environment. If you want more information, here's a good document to actually download. Again, FEMA, it's free. There's the link. Let's transition into chapter 4 of our document and look at some of the design and construction features that are very important for achieving good seismic performance in our building stock. So structurally, we've got our structural elements, our columns, our beams, our roofs, our floors, our foundation systems. That's what we consider our structural components. Everything else associated with that building, we call non-structural components. And so that's the exterior cladding on the building to provide a sealed environment. That's all our MEP systems inside the building to function and provide a nice, comfortable environment. And then whatever function we have for that particular building, be it office, be it manufacturing, hospital, police, emergency operations center, whatever, that's function. Those components are all non-structural components. It's a very broad category, which we'll talk briefly about. But building structures, this is what we're talking about in terms of structural components. Important characteristics: stable foundations, continuous load path, adequate stiffness and strength. We need to be looking at redundancy or regularity in our buildings. We need ductility and toughness in our buildings. Our code provisions require this as we go through our structural design. And we also need adjacency issues resolved in terms of separation from existing buildings. So let's take a look at some of these. Foundations must be stable. We need to understand what our soils are, what our building is founded on. If we have the potential for liquefaction, somehow we have to mitigate that potential hazard associated with our building, because the gravity system during an earthquake could actually fail. So we need to understand what our soils are doing in relative to our foundations. Lateral loads can actually overturn our building if we have unstable or small foundation systems. That could be a high wind event, that could be seismic as well. So we need to understand our building's foundation system. We can actually look at our soils and our foundations providing enough lateral resistance to transfer the lateral loads that are being transferred through the building into our foundations. So we need to have adequate strength there as well. Geologically, we need to understand what the soils are. Are we going to get settlement? Are we going to get differential settlement? We have to factor that into our structural design. Do we have geological conditions of our soils that are going to impose other hazards? Are we on a fault? Do we have liquefaction potential? Do we have lateral spreading? Are we on a hillside? Those considerations all have to be factored into our foundation design for our buildings. General types of foundation systems: we have shallow foundations and deep foundations. So shallow foundations, we can have spread footings that are not buried too deeply below the surface. And we can have raft or mat foundations where we found our building columns as we go up associated with those. We can have deep foundations here showing a bunch of piles, and then a mat foundation on top, and then we build our structure on top of that. Next element, a very, very important one for seismic safety, is our continuous load path through the building to transfer our seismic inertia forces within the structure down into the foundation, into the soils. Very, very key component associated with that. And actually, it's one of the first elements in Chapter 12 of ASC 7 that you'll find. It says, must design for a continuous or ensure a continuous load path. If you think of a chain or anchor on a ship or boat, any one of those links break, then you're going to lose the anchor. And that is very analogous to continuous load path. Very, very important element for seismic design of buildings. This kind of illustrates it. We have a building with at rest, so no external forces acting on it, but now we apply an earthquake. And so if we have a continuous load path, our building in the middle just moves and performs dynamically associated with that response, but it's able to transfer all the forces directly down to the foundation. Whereas the one on the right has some vulnerabilities or elements that within our load path that are deficient. And so we can't effectively transfer the forces through it. And so we get localized failures, potentially leading to an unstable building structure to where we then invite collapse. So that's kind of a good summary of continuous load path that we need to achieve for good seismic design performance. Here's an example. We've got a timber roof diaphragm and precast tilt-up walls. Concrete's heavy, so force is equal to mass times acceleration. We have a lot of force being applied from the panel trying to fall outward. And so our connections of our roof diaphragm to that panel have to be adequate enough to actually support and resist that seismic force that's being generated. If we don't, we end up with damage as you've seen here. We lose our bearing capacity for our roof in that localized area. We get partial collapse of the roof and our panel goes outward. In 1971, in the San Fernando earthquake, we saw a lot of damage to a connection for these types of buildings where they had a ledger on the wall and then a roof diaphragm would just nail down to it. And so that was putting our ledger for out of plane response into out of or cross grain bending. And can't do that anymore. The code provisions have changed. You can't do that in terms of adequate diaphragm to panel out of plane response connections anymore. So a lot of lessons learned as well from earthquakes end up evolving and getting back into our building code provisions. Another example is if we have inadequate foundation or structure to foundation anchorage for our buildings. And here's two examples of what can happen where we've got either a cripple wall system or we've got inadequate anchor bolts to our foundation that we can actually, due to the shaking, slide the building or structures off of the foundation. Then we start severing utilities. We start inviting potential fire hazards due to the gas line that's been connected and the electrical line. So we can prevent that by just providing an adequate anchorage system as part of our load path. Our buildings also have to have strength and stiffness. So we don't want our buildings to displace too much because then we're going to start inducing P delta effects where gravity is acting all the time that could be effective in overturning our structure or collapsing our structure. So we need strength to respond to the forces, but we also need stiffness for the building responds within its an acceptable dynamic range associated with that response. We also like buildings that are regular. Nature loves symmetry. So as soon as we start introducing irregular features in our building, we could potentially invite collapse. So our structural engineer needs to do a little more thorough look at the design around these irregular elements. And example here is on the left where we've got pretty regular structure coming down from the roof, and then all of a sudden we're landing on just columns that are below it with large openings. And so all of our force in those walls coming down now have to displace laterally to go down to the elements on either side of these large openings where we just have columns because they're not as stiff. All the load's going to go to the stiffer elements first. We can have buildings with tall first stories. And so our loads are getting higher as we're transferring them to our foundation systems. And then we hit this tall story, which has less stiffness than the rest of the building structure. We can induce a potential forceful collapse due to a soft story condition there. A good example of that is tuck under garages under multi-story building structures. And here's an example from the 1989 Loma Prieta earthquake. Hasn't collapsed yet, but you can see the displacement is laterally to the left in the photograph because all we had was the garage doors restraining the building in that direction with just thin walls laterally into the left to right direction. We can also, if we have irregular lateral systems on different sides of the building, introduce torsion within our building response. And torsion will generally start to tear a building apart fairly quickly. And so this is showing where we've got walls here on all three sides that are fairly solid with very limited openings. And we've got a storefront section on the front to where it's going to be much more flexible in that direction. And we can now introduce torsion in our building response that we have to account for in design. That's required by the provisions. I mentioned nature loves symmetry. Well, nature loves symmetry in that give me a rectangle and give me a square, and I love it structurally. But architects love to design intricate buildings, wings, if you will, and associated with those is different dynamic response of the elements and where they come together at our reentrant corners is where we see a lot of damage associated with earthquake shaking. And so we have to be cognizant of that and design for those conditions so we have adequate force transfer elements in those areas. We also like to design redundancy in our building structures. So think of suspenders, belt and suspenders. They hold the pants up. And if you don't have them, well, you don't have any redundancy and they could potentially fall off. If you look at the photograph here on the right, that's a typical wood frame construction, stud 16 on center, highly redundant, highly redundant. If you pull a stud out, what's going to happen? The load's just going to redistribute to the other elements and be transferred fairly effectively. So redundancy, we like to see that in our building structures for good seismic performance, just in case. Ductility and toughness, we like ductility in our structures, and in fact, for moderate and high seismic regions, our buildings have to be designed with ductility. That's to account for these larger displacements within our building structure, to be able to account for that displacement without collapse and provide safe structures. They also have to be tough enough to withstand those forces as well. Here's a good example of a untough and ductile structure, and that's unreinforced masonry. One of our most vulnerable building types out there today. If you shake them, if you don't, they're beautiful buildings, but if you shake them, they will start to fail fairly early. Doesn't take much in the way of ground shaking to begin to fail these older buildings because of the lack of ductility and toughness within their structural elements. The way to achieve good ductility is through reinforcement for masonry and concrete structures. And so that's why we put that in there. We put it in strategic places where we have higher stresses within our building structure as well, such as boundary elements in our shear walls. Adjacency, we need to worry about our building, new building going up. Is it adjacent to any other buildings? Because the buildings respond differently. So we need to take that into account. Do we need to have enough space? Do we need to attach them together? And then we start inviting additional load transfer between the buildings we have to take into account. So adjacency is very, very important in terms of seismic design for our buildings. Non-structural components, very quickly, dependent on the importance of the non-structural component, the code addresses these in a fairly minimal way, again, for life safety, not for protection. And our non-structural components are more geared toward functionality of our building after an earthquake, to where if you want a higher level of post-earthquake functionality, you're going to be looking more towards seismic design and bracing for non-structural components. The code breaks them down in these general categories: architectural, MEP, and then contents, FF&E. Here's some examples for architectural elements. This is chapter 13 of ASCE 7, where we find these structural seismic design provisions. MEP systems, so here's some examples of what those are: pumps, chillers, ductwork, transformers, all of our electrical equipment. And then FF&E can be whatever function is in the building. Is it a hospital? It's all of the physical hospital, X-ray equipment, everything there, hospital beds, etc. If it's a manufacturing facility, FF&E is all of their manufacturing equipment. So it varies based on our building type and our category. Non-structural systems, ceiling systems. We saw, this is part of an architectural system as well. We saw quite a bit of damage in north. It's associated with architectural elements, soffits falling, large areas of soffits. Think large areas that are supported by the structure have to be able to accommodate the displacement of the building. So very, very important to have that as part of the structural design for that component. Interior components as well, partition walls, they have to accommodate for building displacement as well as their inertial loads. This is showing that we've got some architectural elements or cladding that's attached to our building. Our building is dynamically responding. So is our cladding system that's attached to the building that has to accommodate the displacements of our building, particular building type, else we're going to have failures of the cladding. Here's several examples of some documents that you can download to get more information on non-structural components. The E74 is probably the go-to for both general architectural, MEP, structural seismic engineers in terms of looking at design provisions for non-structural components and how best to manage those. That's an E74. All right, our last chapter 5, let's look at some common structural types here real quickly. The building code recognizes several key building types: bearing wall systems, which is one of our most common types, frame systems, moment frame systems, beam columns. We can have dual systems and cantilevered systems. There's also some that are not specifically detailed for seismic resistance in low seismic regions, basically designed for gravity and minor wind loads. So bearing wall systems, one of our most common. We can have concrete, we can have masonry, we can have wood bearing wall systems. Vertical loads are resisted by the wall systems, light frame, low commercial buildings, warehouses. Here's some good examples for residential, multi-story and single family. We can have some commercial buildings, office and a warehouse, all bearing wall buildings. We can have some taller buildings. And you can see some typical damage there. We've loaded the bearing walls, we've laterally pushed the building on the left, and we're starting to get cracks in those pier elements that are rising or stacked fully up the building height. The one on the right again is our tilt-up, precast tilt-up building where we've lost some panels due to out-of-plane connection failures. We can have building frames or brace frames. And so the interior core does not act as a lateral system for the building. It's frangible, it's metal stud and drywall, if you will. So all those elements are gravity. And then we have our lateral bracing, our braced frames that are actually resisting our seismic forces from our diaphragms and then transferring those vertically down to our foundation system. So we can have steel, we can have concrete, masonry, and wood, all in this for building frame systems. Here's an example of an exterior skeletal frame that's exposed. We can have moment frame systems. So this is a function of our connectivity between our beams and our columns in terms of laterally resisting the forces being applied by an earthquake or wind for that instance. Again, our cladding system doesn't contribute to our lateral resistance. We're not considering it, as well as our vertical core. It's all frangible materials. It's just a function of our frames and how many do we have for our joints. Here's a good example. The taller section of the building you see here are the moment frames. If you go to the left, you'll see that we don't have moment frame connections associated with that next column on the step down of the building height. These are very flexible, by the way, versus bearing walls, shear wall buildings, as well as brace frame buildings. So moment frame buildings with just column beam connections tend to be much more flexible. They move a lot more than our other, they have less stiffness than our other building types. They offer more free space inside for architects to put stuff, but as far as flexibility go, they are more flexible. We have pre-engineered buildings, and these are light framing. They're single story. There's actually 2 lateral systems associated with these buildings. There's moment frames in the short direction, and in the long direction, we end up having some level of tension bracing, either cables or rods, tension only bracing. So you'll see X braces in those along the length of those buildings. Seismically, they generally perform very well. We can have dual systems. So we can have a combination of bearing wall along with shear wall systems and frame systems associated with it. Well, we'll see those are typically on high-rise buildings. They're going to have the elevator or stairwell cores be shear walls, and then the perimeter framing on that structure around the cores is all moment frame type systems. And so they're sharing some of the loads based on the dynamic response of those. Cantilever column structures, again, low rise, parking garages, carports, that sort of thing. Generally poor performance in earthquakes for these types of structure types. We usually don't see too many of those. So our lateral force resisting systems, within the building code, based on our seismic design category, which is going to be presented in part B later, we have ordinary structures, which is no special seismic detailing for response. That's in our lower seismic shaking areas of the country, lower seismic design categories. Then we step up a little bit to intermediate detailing for our structures, depending on the type of lateral system we select out of Chapter 12 in ASC 7, and the type of system we select. There are intermediate systems that we can utilize as a structural engineer for designing a building. Then there's the highest, which is our special. And so high level of ductility in these buildings and a much higher level of performance out of these types of buildings utilized in our higher seismic shaking regions of the country. So with that, and I'm surprised I finished because there's a lot of material here and I went pretty fast. Our last poll question here before we summarize everything is the following. Select the answer which is most important in terms of elements or features that we look at for good seismic performance in our building stock. So read through those and pick which one is the best. Is it having just adopted and enforcing a building code? Is it designing for a continuous load path? Is it looking at non-structural component performance in our buildings? Or is it all of the above? Give you a few more minutes here. We'll have a little bit of time for questions too, which is great. Majority of you, if you haven't voted yet, are selecting all of the above, and that is the correct answer. So we do need a current building code that's adopted and enforced. Key point. One of the key elements is continuous load path to transfer our forces. And then non-structural components for good building post-earthquake functionality is also important. And so all of those above are good features or features that we'd like to see incorporated into our building design for good seismic performance. All right. Get rid of that. All right, in summary, key elements of building seismic safety. Earthquake hazard and soil conditions need to be understood. That's our in chapter 1. Community needs to adopt and, more importantly, and almost should be underlined, enforce the seismic provisions within the building code. Very, very important. That's incorporated in chapter 2 of our P-749 document. Looking at community resiliency to natural hazards, particularly earthquake, can think in the context of resilient design. What is our acceptable risk under current code seismic design provisions, and should we elevate that performance? Is the context there, and that's in chapter 3. Chapter 4 speaks to some of those features within our buildings we need to ensure that we have good seismic performance during strong shaking in our buildings, and that's reflected in chapter 4. And then chapter 5, some of the different lateral systems within our structure types that are key to good seismic performance. And these latter two, chapter 4 and 5, the elements in there are expanded upon in part B that Ron Hamburger is going to be speaking about when that comes about. So with that, I'll open it up for questions. We have about 10 minutes, which is great. I'm happy for that. I'll turn it over here now, if I can do that.
Thank you so much, Mike, for this wonderful crash course, I would say.
Yes. Good term.
And yes, you have laid the groundwork very well for the next webinar. We would like to thank you for this. And we would also like to thank ATC and FEMA, especially Ginevra and Patya, for making this webinar happen. With that, I would take a couple of questions. So the first question is regarding the trigger. What code should we use when we have the trigger, like an occupancy change?
Oh, within the IEBC, that's one of the triggers is occupancy change. And in the IEBC, it also defines what you have to do in terms of design, structural design for the building. There's also fire safety in there, elements that are key, not only just the structural aspects of it. But on the structural side of it, if you do have an occupancy change, it's basically going to force you to reevaluate the entire existing building and bring it up to current code provisions. So you're going to have to use the seismic hazard that's associated with the current code, not what was used when the building was first designed, which could have been back in the 80s, 70s, or older. And you're going to have to retrofit the building to essentially bring it up to code associated with that. So that's a pretty significant, particularly for an older building, a pretty significant financial investment, if you will, for that trigger. So it's, everybody needs to be talking about that, the owner particularly, to understand the, you know, what's involved in that decision. But the IEBC defines it. The IEBC defines what you have to do. It essentially says, hey, if you do this, you're going to have to go make sure this building is compliant with the IBC seismic provisions. That's what it says.
Yeah, thank you so much. There's another question related to the same thing. So what is the difference between IEBC and like the ASCE 4117?
The IEBC is the code for existing buildings that trigger the various upgrades that may be necessary for that building. 4117 is the evaluation and retrofit standard, which is performance based. You can select whatever hazard you want. You can select whatever building performance level you want, and then go through 4117 and actually design the retrofit associated with it. So you can select the code level provision for new buildings within the objective of 4117 to actually design your retrofit. Okay. Pretty sure I'm stating, Ron would answer that better than I, but I'm pretty sure that is correct. You can do that versus go through and evaluate it as if it's a new building using the IBC and ASC 722, for instance, in that regard, and be compliant.
So if I understand correctly, the IEBC is like the minimum standard for existing buildings?
It's the code that's triggering what you have to do if it's adopted by the jurisdiction. Okay, the tools to use now become 4117 as a tool or resource to utilize to achieve that objective. Okay.
Okay.
IABC says bring it up to code because you changed the occupancy. Okay, well, how do I do that? I think that's a question that's being asked. 4117 is the tool or resource to utilize to do that. Again, you got to establish your performance objective, which is incorporated within 4117. That meets the building code.
Okay. There's another question regarding the building codes. So in United States, do we have to have a recommended building code for at the local level?
You have to. It depends on where you live. The answer is no. It depends on the jurisdiction to whether they have adopted a building code and enforce it within the jurisdiction. If you can imagine small rural communities, they don't have a building department. And so generally what happens is it defaults to the county level. And so if it's a rural county, that the rural county may not have a building department as well to adopt and implement a building code. And then if it's not in the county, it could go up to the state level, where the state now has a adopted building code. Okay, then it's up to the state in some capacity in their building department to enforce it, which, you know, how they have a building department big enough to enforce all the provisions within the state? Unlikely. Okay, but that's sort of what you'll see is larger municipalities and cities have a building department, and they will have adopted a building code and enforce it. And so your smaller communities do not. Generally, that's what you'll find. California has a state adopted building code. Missouri here, we do not. Missouri has a state adopted building code. Missouri, we do not.
I think that's a very good.
It depends.
I think that's a very good.
Now you are free to use in those areas whatever you want. And I know out here in Missouri, with architects and the structural engineers, when we get projects out in the rural areas, what we do is we just default to the current code and ASCE 7, and that's how we design the building, because that's part of our professional responsibility as well. So I mean, so you're sort of getting it, you're just not getting it in a rigorous fashion where you've got a building department that's involved, that's plan reviewing and doing inspections.
Yeah, I think that's a very good answer to this question. There's another question regarding the non-structural elements. So how can we perform the seismic analysis for non-structural elements? How do you do that, like in your office?
Chapter 13 in ASC 7 has the provisions for non-structural components. And so you can, the seismic design provisions are all there. So you just, they're broken down to architectural MEP systems. Contents, you know, normally contents will fall under the exemptions. And it's just like our risk seismic, our acceptable risk. If we have a higher seismic design category our building is in, then we're going to be triggering more of the seismic provisions in Chapter 13 to design for non-structural components than we would if we're in a low seismic shaking environment. So for instance, category B, seismic design category B triggers architectural elements in a few cases, but mechanical electrical components are totally exempt. You go to seismic design category C, which is a moderate level of shaking environment. Normal MEP systems that are not part of life safety systems like fire protection, emergency egress, part of an emergency generator system that's providing emergency power in the building, those are exempt. You don't have to do anything. So it's only those life safety systems in category C that you have to seismically design bracing and anchorage for, according to Chapter 13. And then D, E, and F is our highest seismic design categories. And there you're triggering everything. There's a few exemptions you can still do, but you're designing for all of it. So it's fairly succinct in terms of what you have to do. The bigger challenge for non-structural components is who does this? If you know, electrical engineer is responsible for the electrical systems. Does an electrical engineer have seismic design experience, either in school or real life? No, he doesn't. So everybody thinks it's the structural engineer that's supposed to do all this stuff. Well, does a structural engineer know about electrical systems? Does he really know, you know, in terms of functional performance after an earthquake, how that piece of electrical and mechanical equipment are going to behave? Does he know how relays chatter that could affect performance and trip things offline, downline? No, he can design anchorage. So non-structural components fall into sort of a gray area or a gap in terms of really achieving good performance out of non-structural components. You don't have anybody that's trained, educated to do just seismic design for non-structural components. Very rare, very rare. You'll have some of the structural engineers, such as myself, that we know a lot about it, and we do it. day to day. California OSHPD has forced structural engineers to become involved with non-structural components for healthcare, for hospitals. Outside of that, it's pretty non-existent.
Yeah.
I'm sorry, I had to
No, I completely agree. Like it is not very prevalent to have the non-structural design.
well, I mean, look at your core classes in college. Is there one for non-structural seismic design?
No.
You're going to be tough to find it.
There's a question regarding your least favorite type of structure, depending on the redundancy.
My least favorite is unreinforced masonry in moderate or high seismic shaking regions. And I'll tell you why. Earlier in my career, I went around the world, literally looking at damage to buildings from earthquakes. And my worst earthquake was Armenia in 1988. And 25,000 people died in the Armenia earthquake due to primarily unreinforced masonry buildings collapsing. And so I have a unique appreciation for the vulnerability associated with unreinforced masonry buildings that almost haunts me to this day in terms of their vulnerability. And in fact, when I go to, I was raised in California and educated out there, so I still have family out there. So when I go out there and we go out to dinner or any place, and you go to smaller downtowns, they all have unreinforced masonry. You can walk in and look to see whether it's been retrofitted or not. And I literally have a caution that flares up in me when I do that. Because if I feel any shaking, I'm gone. I'm out of there, or I'm duck covering and going on. Any building that does that to me is that building type. Other buildings I feel safer in, and I don't have that sort of reaction associated with it. So for me, it's unreinforced masonry. It doesn't take much shaking. It doesn't take the big one. It doesn't take the moderate one to start causing a collapse to unreinforced masonry buildings. That's how vulnerable they are. That's just me.
Yeah, I think that's a very good answer. Like I would also agree with the unreinforced masonry answer. So we have another question regarding the existing building code. Does IEBC address industrial structures? And in that case, who is the AHJ in these situations?
Industrial structures, they're still under the control of the AHJ, but oftentimes what you'll find is the AHJ will defer at times to the owner of that manufacturing facility. What you'll find is that the manufacturing facility there, if it's their own facility, say a refinery or something like that, they have their own internal engineers that do the engineering and design. And so in those instances, oftentimes you'll find the AHJ just deferring to their enforcement of the building code with little oversight in that regard. You got to understand, major manufacturers are going to want to put up something that's going to collapse in an earthquake. They're going to incur a huge amount of liability if they do that. So they're going to want to do the right thing, but they generally have their own in-staff engineering group that does, the designs for them.
Yeah. Thank you so much for all these answers. We have just one last question. It is more related to the geotechnical engineers, but I would ask you. So what is the behavior of P and S waves in saturated compressive soil?
That's over my head. I'm not a geologist. I always say geologists address everything below grade, structural engineers, everything above grade, except the foundations. We tie in there. The P waves are faster, the S waves are the damaging ones. I know that. But in that particular soil type that you referenced, I can't tell you whether it's worse or not.
Yep. Thank you so much for all these answers. With that, I would hand it over to Elizabeth, and she would do the closing.
All right, thank you again so much, Mike, especially, and also everybody at ATC and FEMA and the Student Leadership Council for this excellent presentation. I am just launching a poll that I would be grateful if everybody could take a quick moment to respond to this post-webinar survey for us. And also remind you, the slides are in the chat if you'd like to download those now while you have a chance before we end, and also to sign up for next week's session for the second part of the webinar. And I'll just put the link to that in the chat again.
Did we get a lot of questions? Are we going to consider answering some of those and sending them out via email?
I think we were able to answer pretty much all the questions. There were a couple of double questions.
Okay, good. Part B is May, I can't remember.
That's May 5th, so next Thursday. It's the same
May
time, but it's a slightly longer session. And I am just getting that link right now to put in the chat here for those of you who haven't signed up yet. So please remember to join us for that.
That'll be very technical. So if you're interested in the technical aspects of the design provisions, tune in.
All right, thanks everybody so much for your feedback and for participating today. I'm going to go ahead and end the session now. Thanks again and see you next week.
Great, thank you.